Now we continue with the presentations of participants. You are the first one in line?
Yeah. All right, so first I want to thank the organizer to give me the opportunity to attend this spring school, which has been a very good experience for me. So my presentation is about clustering popularity adjusted stochastic block model. This is a joint work with my advisor, Dr. Mariano Pensky. So one of the problems in machine learning and data mining is clustering, which I'm pretty sure most of you are familiar with. And many data set can be represented as a network of interacting items. So one of the first features of interest in such networks is to understand which items are similar. And clustering actually can help us to do that one. So for example, if you consider this network, so we have a bunch of nodes and edges which connect those nodes. So this is a scrambled network. So we can use some clustering to detect these communities, right? So for example, these are some of the real networks, citation networks. So we can consider papers as nodes and citation as edges. So this is considered as a directed network. So email or social network, Facebook, Twitter, all of these are examples of networks. So in biomedical science, we have interaction between proteins or interaction between regions of the brain. So these are all some real network examples. So now let's start with an undirected network and nodes and no self loops and no multiple edges. So adjacency matrix of these kind of networks is a binary matrix, which is symmetric. Aij equals to 1 if there is an edge between I and j, and otherwise Aij equals to 0. So we assume that Aij has Bernoulli distribution with probability Pij. So this probability actually plays a very important role in our model. So the model assumes that we have k distinct communities, and we have community assignment C I equals to k if the I node belongs to the k community. And one of the features of the model is the popularity of node across the communities, which is defined as the number of edges between a specific node and a specific community. So before I just talk about the model, popularity adjusted stochastic block model, let me just mention two simpler models. So a classical random graph model is a stochastic block model, is called SPM, which is a very simple model. And under this model, probability of connection between nodes is constant, depends on just the community to which they belong, those nodes. So if we consider the probability matrix, you consider the, let's order all of the nodes in their own clusters. So we have this structure. So we have a block matrix, block probability matrix. So each block is a constant. So we have B11 for just probability of connection of nodes in the first community. So diagonal blocks show the probability of connection between nodes in their own community, and the rest of it shows, for example, this one shows the probability of connection between nodes from the first community and the second community, and so on. So we can see in real networks, this is not a good model actually to just model all of the networks. So in real networks, you have only a few nodes with the high degrees, and the rest of them are have low degrees. So that's why this model, SPM, fails to explain the structure of many networks. So there is another model, which is called the degree-corrected block model. So this model tries to address this deficiency by letting, by multiplying each block probability by some weights. So here is the structure of the probability matrix. So we have we are multiplying, instead of one vector, we are multiplying by some weights. So these are, this is a vector, this is another vector. So we get a block here, and in total we have just a block probability matrix. So when theta, that weight is large, so that means the corresponding, the node corresponding to that theta is popular than the other one, which is smaller. So if you consider two nodes in just one community, so the one which has a larger theta is more popular than the second one across all of the communities uniformly. So which is the issue, right? So that means this model also can't explain, in fact, many real networks properly. So now let's go to the model that we want to do clustering on. So this model is called the popularity adjusted stochastic block model. So introduced by Sengupta and Cheng. It's kind of pretty new, and it's not well studied network model. So it generalizes SPM and DCBN that I mentioned. So under this model, so the probability matrix has this form. So the Pij is the product of two parameters, which are called the popularity scaling parameters. So if we assume that we just arrange all of the nodes in their own communities, so probability matrix has this structure. So we have, again, we have block probability matrix, which lambda is a n by k matrix. So now, before I mention about the clustering, so the authors of this paper actually they used some clustering method, but that method only they just did the simulation. It works well only for just two communities, two clusters. But real networks, we are interested in do clustering just with more clusters, maybe 3, 4, 5, and even more than that. So here, based on the structure of this probability matrix, we just suggest that we can use subspace clustering, which is widely used in computer science, computer vision. And so subspace clustering is designed for separation of points that lie in the union of subspaces, right? So since matrix P is constructed by k clusters of columns or rows that lie in the union of k distinct subspaces, each of the dimension k, we can actually use subspace clustering to just cluster the networks that fit this model. So let me just go back to this. If you look at this probability matrix, so just look at this block column. So this one has rank 1, this one is rank 1. All of these are rank 1. So if you consider this column, you're going to have a column of rank k. So you can consider this one one subspace of dimension k. And we have similar pattern here. We have subspace from dimension k, subspace from dimension k. We have k subspaces, each one has dimension k. So that means we can use subspace clustering to cluster the networks that fit this model. So now, basically, subspace clustering relies on some affinity matrix, right? So we're going to use here, we're going to use the sparse subspace clustering to just find that affinity matrix. So the idea of this sparse subspace clustering is writing every point as a sparse linear combination of all other points. And we minimize the number of non-zero coefficients here. So when we have noise, we add L2 norm to that objective function. And the last one is equivalent to this optimization problem, which L is the maximum number of non-zero elements in each column of W, matrix W, coefficient matrix. When we find W, we can form the affinity matrix. Here, this is the affinity matrix. And we can apply spectral clustering to find the clustering matrix, which I just used Z as the clustering matrix. So this is a procedure that we can use to find the clustering. We can cluster the network. So now let's look at simulation. So we generate the data, we generate the networks that follow PABM, this model. So we assume that we have k known clusters, and we also assume the clusters are perfectly balanced. So we have n over k nodes on each cluster. And to make sure the nodes on the same community have, most of the nodes in the same community have the larger probability, we just multiply on the diagonal block of this lambda by one parameter omega, which is between 0 and 1. So in general, matrix P that I showed you in last slide is not known, okay? So we can use actually this procedure to estimate this probability matrix. So, since this one takes a lot of time, I didn't include the slide. So the idea is just when we find the clustering matrix, we can order nodes based on their clusters, like block matrix. And then we use rank one approximation of each block. That one gives us the estimation, the estimator of the probability matrix P. So for finding the errors, so we have two errors, estimation error and clustering error. So this, we can use this one for estimation error and this one for clustering error. So now let's look at the simulation. So when we apply, actually, let me just mention this one. So we are comparing our results, sparse subspace clustering that I introduced here, with the results that can be found using a spectral clustering. A spectral clustering is one of the well-known approaches to cluster the networks. So that's why I'm just comparing the sparse subspace clustering result with the results obtained by the spectral clustering. So we use spectral clustering with SC, and we are using dashed line for spectral clustering, and solid line shows that the result for sparse subspace clustering. So the top one, the top plot shows the errors for clustering error, and the bottom one is the estimation error. So we compare the lines with the same colors. So as we can see, as the diversity, as I mentioned before, omega, I'm not sure if it's clear or not. So omega just controls the diversity of the network. So as the diversity of the network increases, the difference between these lines is getting larger. So that means sparse subspace clustering gives us better results. So, and we have the similar pattern here. So all of these networks, so these show the number of nodes. All of these networks have 4 clusters. So we have a similar pattern for the networks with k equals to 5 clusters. So let me show you what I meant by the diversity. So here we have the adjacency matrices of 3 networks. Each one has 420 nodes and 4 clusters. Okay. So omega, as I mentioned, just controls the diversity. So this one corresponds to 0.5, 0.7, and this one 0.9. So here you can find these 4 clusters pretty easy. You can see it. Here we increase the diversity. Still you can see it. But here it's not easy to detect those 4 clusters by eye, at least. So, but our simulation showed that sparse subspace clustering actually can detect these 4 communities way better than spectral clustering, right? So one of the problems in clustering always is what is the number of clusters? What is the true number of clusters? So here in this model, we can use the estimator of the probability to just estimate the true number of clusters. So we can just solve this optimization problem to just estimate that true number of clusters. So I summarized the just the result for a few networks. So we have 6 different networks, and each one, the true number of clusters is 4. And so you can see with a reasonably high probability, the previous optimization problem I showed you can find that can estimate the true number of clusters. So we have similar results for 5 clusters. So when we use that one. So, and the last part, I want to just mention one example. So just suppose you have this network, butterfly similarity network. So there is an edge between 2 butterfly if there is a similarity between them. Otherwise, there is no edge. So we want to just cluster them based on their similarities. So when we apply our method to this network, we see that the sparse subspace clustering gives us 89% of accuracy, while spectral clustering is correct only in 64% of the cases. So for finding those communities. So that means SSC works better than spectral clustering. Of course, as I mentioned, sparse subspace clustering is kind of costly because we have to find just coefficient matrix and then apply spectral clustering again. But so far, so this is the best method we found. So to just find those communities. And at the end, these are the important references that I use for my presentation. And thank you.
Thank you. Comments, questions? Yeah, Peter.
Yeah. So I saw in your example, actually, when you wrote that, you kind of assume that in each community you have approximately the same amount of elements.
Yeah. For simulation, yeah, I did. But for this example,
to have that different?
But for this example, no, these they don't have exact. They don't have the same number of.
No, but is it a problem if you have just one is 10 times bigger than the others or
So
something like
it's
that?
kind of biased. If I want to do that one, so how am I gonna just create that one? It should be just some random thing. I have to create an algorithm. So again, that algorithm just may not be true. So just we actually running just that program just 50 or 100 times to get the accurate result. But for that one, as long as we have enough nodes in the community, I don't think we have a problem with that one, because this example doesn't have, this is a real example, doesn't have the same number.
No, I'm not talking the same, I'm talking one community has 10 times more than the other, so
in simulation or?
No, just the example. There's sometimes you have big community which
okay. So
is similar, and then some small communities which are.
But it works. So
okay.
As I mentioned, as long as we have enough points in one community, it works.
Okay, I think we should move to the next presentation. Thank you very much.